Yeah, so good morning, everyone. I'm going to talk about some relational thing. It is commonplace to say that there are many differences between general relativity and quantum mechanics. And one of the goals is to find a bridge between these two fields. And this bridge would be called quantum gravity. And to look for quantum gravity, one can look at differences, but it's also interesting to look at common points between the fields. And this is what people do, for instance, when they are studying black holes or the early cosmology. Now we'd like to look at common points, but at a more conceptual level, and try to think about a notion, relationality, which appears in both realms of physics. It appears in general relativity, where it takes the form of diffeomorphism invariance, but it also appears in quantum mechanics, at least if one is ready to buy some relational interpretation of it. Now the question I want to ask in this talk is, are these two kinds of relationality actually the same? Or maybe to ask it a bit more precisely, if we have a theory of quantum gravity, what kind of relationality should we expect at this level? So relationality is a very general notion. So it's very easy to get confused by what this term means, especially when we are trying to bridge different communities which have different ways of seeing things. So we have to be careful about what we mean. So to start with, let's try with an easy example that everyone is supposed to know, classical mechanics. And so let's read this quotation. If anyone is moved in a ship and he imagines that he is at rest, then should he see another ship which is truly at rest, it will appear to him that the other ship is moved. This is so because his eye would be completely in the same relationship to the other ship, regardless of whether his own ship is at rest or the other moved, or the contrary situation prevails. Question: is this Galilean relativity? So answer, not really. Actually, this quotation is from a guy named Buridan, a French philosopher from the 14th century. That's more than 2 centuries before Galileo. But it looks very close to what we would like to say Galilean relativity. This kind of relativity, I will call it kinematic relativity. Actually, it's the simple observation that whenever I want to describe motion or position, I have to do it with respect to some other reference system. This is a fact, but it's not Galilean relativity. Let's come to this. So this first observation about kinematic relativity raises an issue. And this issue is called the fundamental problem of motion by Julian Barbour. The fundamental problem of motion is, if all motion is relative and everything in the universe is in motion, how can one ever set up a determinate theory of motion? The answer to this problem is given by Newton in a thought experiment, which are the Newton's bucket. So I have a bucket filled of water. And in both situations, there is no relative motion of the water with respect to the bucket. In both cases, here and here, the water is still in the bucket. There's no relative motion between the two. Nevertheless, you can say, just at looking here, which one is turning and which one is not. You know that this one is turning. You know it because you look at the shape of the surface, and you know intuitively that it's turning. But Newton says that it's turning with respect to what? Because we have both kinematic relativity. So if I talk of a motion, it should be motion with respect to something. And Newton says, yes, it's a motion with respect to something. And this something, I call it space. I call it absolute space. And since now I have absolute space, I can talk of absolute motion. But absolute motion is just a shortcut for motion with respect to absolute space. And now I can talk about Galilean relativity. Galileo says, so you see, I reverse chronological order because I think conceptually it's more clear. So now Galileo says, okay, maybe you can detect absolute rotation, but I claim that you cannot detect absolute rest. Or more precisely, you cannot distinguish between absolute rest and absolute uniform straight line motion. This is a dynamical statement. So to sum up, in classical mechanics, we have 3 levels. We have a layer of absolutism in between 2 layers of relationalism. The first layer is kinematic relativity, this observation that we need to refer to something to describe motion. From this and the experiment of buckets, we deduce the existence of absolute space. And on top of that, we make a dynamical claim, which is Galilean relativity. So you see, even at a theory which we are supposed to know well, when we are trying to see precisely what is relational and what is absolute in it, it's a bit tricky. So that now let's move to.
Why do you call it dynamical?
Because the absolute space. Why is it important? It's important because Newton solves the fundamental problem of motion because he says, I can give you an equation, which is Newton's law, which gives you the dynamic of the motion with respect to absolute space. And then Galileo put a restriction about the kind of motion that you can actually detect.
Symmetry in the solutions to the equations of motion.
Right. So now let's move to general relativity. So in most textbooks about general relativity, the standard picture of space-time is this one. So what is space-time? It is a manifold. And on top of this manifold, you have a field, which is the metric field. So we have the image, this image in our head. We have a grid, which is a bit curved and deformed by the presence of mass. Okay. This picture is problematic because it lets us believe that space-time is actually made of a continuum of points. But this view is false. This view is not correct. I'm going to try to explain a bit why. I would like to take again this picture of 3 layers. But I'm not completely sure if this is correct. So this is also a question for you, if we can keep this picture in general relativity. So in general relativity, we still have a kinematical, a form of kinematic relativity, which I call general covariance. In fact, it is the possibility to choose any grid on my manifold. That's general covariance. It's also passive diffeomorphism. It's the possibility to choose any coordinates to describe space-time. And then I also have an upper layer, which is Galilean relativity, but it's Galilean relativity extended to accelerated motion. And so it's kind of diffeomorphism invariance, that is to say active diffeomorphism. Conceptually, those two are different, but formally they are the same in the formalism. And since they are the same formally, it leaves no room for a notion of absolute space. In fact, in between, to see it clearly, one has to go through the whole argument that I have no time to recall, unfortunately. But the upshot of the whole argument is that the space-time points are not points of the manifold. So in general relativity, we don't have this layer of absolutism. We are more relational. But the way I formulate this relationalism by saying that I cannot say that the space-time points are the points of the manifold is like a negative way of formulating it. It's hard to find a positive content of this relationalism. How can I formulate it? The relationalism of space-time in general relativity. So one way to say would be I could say, well, in fact, in general relativity, there is no space-time. I should only look at distances between material points. But this view is not correct. It's not correct because there are vacuum solutions of Einstein's equations. And in these vacuum solutions, you can have gravitational waves which can have huge effects because they have a lot of energy. So maybe a more correct view is to say that what remains of the absolute core of space-time in general relativity is an equivalence class between solutions of Einstein's equations. And two representatives of the same class are related by a diffeomorphism. If I take one representative, a metric, J mu nu of x, by itself, it does not mean much. If I want to extract information, an observable, a number that I can really observe from this representative of the metric, I need to use something else, like another field, a scalar field of matter. And in this sense, I touch at the relational core of general relativity, which is that this variable x by itself means nothing. If I want to give a meaning to this to this coordinate x, I need to refer to something else, to another field, a matter field. So that's it for general relativity. And now let's move to quantum mechanics. 5. Okay. So the fact that quantum mechanics exhibits relational aspects is not universally acknowledged. One reason for this may be that it's not explicit in the word, quantum mechanics. Like in general relativity, it sounds like natural to see some kind of relationality. In quantum mechanics, what's explicit is quantum. That is to say, the discreteness of it. But the relational aspect is not explicit. We had to wait for quite a long time before it was noticed. That's 1957 by Everett in the relative state formulation of quantum mechanics. So Everett proposed the following experiment, which is a thought experiment, which is also called Wigner's friend, which has been much discussed after this. So I have an observer, B, which is doing a measurement on C. And he is describing the state of C. So this state is given by, here I'm using density matrices. So this is the initial state. And then the final state after the measurement is a projection of the initial state. So you have a collapse, a non-unitary evolution. Now if I take a second observer A, and which is not interacting with B and C, but I ask him to describe the system C. At initial time, it's the same state for C, but then the evolution is different. So the evolution would be given by a trace over the B degrees of freedom of the unitary evolution of the overall B and C system. That's a different time evolution. That's a different state. It's not the same state. So this has fueled many discussions, especially this has fueled the many world interpretations. So in many world interpretation, they would say, well, it's not the same state. Why? Because when the measurement happens, in fact, the world splits in two, or splits in many branches. And in each branch, I have a different result. So everything is consistent. So it's a bit strange now after years. The many worlds interpretation have been refined, and so now people would say, actually the splitting does not happen everywhere. It happens only locally, and then it expands. So that's a bit more reasonable. But still, to me, many worlds interpretation commit the same kind of mistake as Ptolemy was doing. That is to say, attributing to the world properties which are in fact only perspectival. You see, Ptolemy was looking at the planets and he was seeing epicycles. And he was saying, okay, the planets are making epicycles. But no, in fact, what he's saying, it's himself turning around the Earth. So he was attributing properties to the planets which were only perspectival. And to me, that's a kind of same mistake they do. They say the world is split in many branches, whereas to me, or at least what relational interpretation would say, is that it's only a matter of perspective. So the relational interpretation, introduced in this paper by Carlo, would say, okay, I agree, there are two different states, but that's okay. Because the state is only relative to the observer. And so the fact that two observers describe the same system with different states is just fine. So this raises problems about the ontology, about quantum mechanics, about is this the systems or the relations between the systems which are primordial. But I guess I have no time to talk more about this. Is this strange? Is this strange relational? Well, maybe yes, maybe not. If you see this cup, for instance, for you it's a left-handed cup, but for me it's a right-handed cup. Okay? That's kinematic relativity. The fact that to the question, where is the handle, you answer left, I answer right. My state about the cup, our state is different. So that's kinematic relativity, and that's not surprising at all. And I think that's part of the relational interpretation. What is surprising and disturbing is when we are talking not about external degrees of freedom, but about internal degrees of freedom, like the color of quarks. It is strange to say that the color of a quark depends not only of the quark, but also of the observer who is looking at the quark. These are for internal degrees of freedom, and here it's strange. But this really says that the property, red or green, is not only a property of the system, it's the property of the relation between the observer and the system. Okay. That was quantum mechanics before general relativity, now quantum gravity. The question is, are the two kinds of relationality the same? Because in quantum gravity, a priori, we should expect to see relationality coming from both directions at two levels. General relativity, quantum mechanics. But maybe they are just the same. So it's tempting to say that it is the same, but unfortunately I don't have any theoretical formalism to say it in a precise way. So I can only say for now that the concept of relationality are still vague enough for this not to be false. But maybe it's interesting to try to pick one theory of quantum gravity that we have and to see how does relationality appears in this. So let's try with the covariant formulation of loop quantum gravity, spin foams. Yeah. Okay, that's the last slide. Okay. Okay. Yeah, I'm sorry. So what is the interpretation of spin foams? Sometimes I have the feeling that there is no consensus about the interpretation of spin foams, but I'm actually only aware of one physical interpretation, which I find convincing, and so this is the one I want to discuss. it comes back to some ideas of Robert Huckel in a more general framework, which is called general boundary quantum field theory. So how is this working? I start with a system. What is a system in this case? A system is a 3D surface of space-time. And then in loop quantum gravity, I can describe this 3D surface by a spin network state. Now, I'm going to attribute to this spin network state an amplitude, spin network amplitude, to one state. Two questions. How do I compute the amplitude? What does it mean? So first, how do I compute it? I compute this spin network amplitude as a sum over some other amplitudes, which are spin foam amplitudes, which these are spin foams whose boundary is made of the spin network. And then I can compute the spin foam amplitude. This is standard procedure. Also maybe not so easy, but we have formulas for it. So the spin foam amplitude gives me an approximation for the spin network amplitude on the boundary. If I want a better approximation, then I take a spin foam which is more fine. Okay, so that's how I compute the spin network amplitude. Now, what is its meaning? The meaning given by Robert Huckel is also in terms of probability, but there is a difference with standard QFT. In standard QFT, I have amplitude, but it is actually a transition amplitude between two states. Here, it's not a transition between two states. It's just the amplitude of one state. So I cannot, how do I interpret it as probability between? And Robert Huckel says, yeah, okay, I can still see it as a probability, but that will be a probability between two states of knowledge, which I denote like this, probability of A. So it's a conditional probability. And by introducing this conditional probability, I get rid of some absolute aspect which were still present in standard QFT. This interpretation is much more relational in two senses. It is relational because it does not need a special time slicing as we have in standard QFT. It is generally covariant. And second aspect, it talks about state not as states which are realistic about what there is in the world. It's really state of knowledge, so close to the relational interpretation. So in these few minutes, I've talked to you about several aspects of relational aspects in many theories. It's still ideas which are a bit vague, and I'm not sure about everything I've said, but I'm very looking forward to hearing what you have to say about it and to hear your reflections. Thank you.
Okay, Marco, then Chesley.
So I wanted to just go back to the statement about general relativity and the whole argument, and that the points do not exist. Yeah. So well, the whole argument doesn't. It tells you that you cannot identify individual points in space-time because of diffeomorphism symmetry. But to say that individual points do not exist is, in my opinion, a bit too strong a statement, because there are aspects of individual points that are diffeomorphism invariant.
Right.
It can be. So it's one thing to say that you cannot observe individual points, and it's another thing to say that they do not exist.
Okay.
So
Yeah.
in my opinion, observability and existence are two different things. So I just wanted that as a small comment.
Yeah, I think I agree with what you say. Yeah. The wrong point would be to identify space-time points with points of the topological space which underlie the manifold. This is the wrong take, which one should not do. And this is the wrong image which I think is given by this picture. When we are seeing this picture, we are really thinking that there is something here, and that we can, for instance, think of the motion of just one particle moving here. But that's not observable, so yeah.
There's no the chairman,
Oh,
but
I don't know which.
so I was intrigued by these two pictures that you put next to each other about a cup left handed and right, and the color of the quarks. So I wonder, and then I have a small comment. I wonder, do you really think that there is a fundamental difference in observing these two properties?
Yeah.
And then I would like to add about the relation aspect, at least for the cup, left-handed and right-handed, which I'm sure you're aware of, but I think it's important to say. And that's that when you show out this cup, then it's really relational. So we have different statements about that, but still in classical physics, we can assume that there are some features, objective features of the cup and our position in space with respect to the cup, where this relation aspect will come as emergent.
Right.
Whereas in quantum mechanics, even a mere assumption that there is this objective property runs into the problem of the invariance. So it's a fundamentally relational aspect, not reducible to any objectivity outside.
Right. So I think I agree with you for the first question that there is no fundamental difference between internal and external degrees of freedom, but that this is only artificial difference. But conceptually, this is very easy to think for us that this is relational. This is very uneasy. Formally, maybe it looks the same, but conceptually, that's the difference. Then, as regard to the question, your second question, you're right. There is a relational aspect in quantum mechanics, but that is not all there is about quantum mechanics. There are other things. There are probabilities, there are discreteness. So, that's a question about the ontology, the difference between the systems and the point of view I have on the system, the relations between systems. What's primordial? Usually, in quantum mechanics, in the way it's postulated by von Neumann, for instance, there is the axiom number 0, which is never said explicitly. It is the world is made of systems. And then we build on this. And we look at properties of systems. My view would be rather that system is a concept which is secondary. System would be an easy way to recast past measurements into something which is easy to think with. And so, for instance, how do I know that this cup exists? What do I call a cup? Well, a cup, I see it by what I access to the cup. In fact, are many point of view on the cup. I see that it's right-handed, it's left-handed, and there are all the rotations about the cup. And so maybe some people would formally say that the cup is the equivalence class of all the point of view I have on my cup. And I think it's a bit funny to say it this way, because a bit maybe too formal, because I've never seen anyone pouring water into an equivalence class. But still, I think it's quite fair to see systems as a reconstruction from different observation. Now, the difference between the cup, which is classical, and quantum mechanics, is the structure I have on this equivalence class. In quantum mechanics, my equivalence class has the structure of a Hilbert space, which means that I can put in superposition different point of view that I have on my cup, which is not the case for the classical equivalence class. The classical equivalence class has a much simpler structure. So I think both classical and quantum mechanics, we have this relational aspect, but in quantum we have more structure.
One quick question from Carlo.
Sorry, two very short comments. It was a great talk. I think you just struck core issue at the foundation of quantum mechanics. One is that you made this distinction between internal degrees of freedom and external degrees of freedom. I think it's very good. If I remember well, it goes back to David Lewis. This terminology is very appropriate. And my understanding is that the main message of quantum mechanics is that ultimately all degrees of freedom are external. So ultimately there are no internal variables. So that's the first comment. And the second comment, and I think we could agree on that reading of quantum mechanics. And the second comment is similar. The other side of the story, GR. I agree it's not easy to capture the relationality of GR. You turn around, but also here, in this environment in which operationalism, it's a common point of view, there is a clean technical way of saying, I think, the conceptual novelty of GR with respect to space-time points, to go back to the question, which is the following. In a pre-generativistic quantum classical field theory or quantum field theory like electromagnetism, the x coordinates have an operational definition. So I can say what I mean by x by saying, 3 meters for that wall. In a generativistic theory, GR or GR plus anything else, they don't.
Right.
There is no operational definition of x independent of the fields, while in relativistic they do. So there is a deep operational difference in what we mean by space-time points before and after the GR evolution.
Let's thank the speaker again.